This is Swathi, working as Assistant Professor in the Department of Electronics and Communication Engineering in Institute of Aeronautical Engineering, Dundigal. Welcome to this lecture. In this lecture, we'll discuss some problems on common base configuration. So the basic contents of this lecture. So we'll discuss some problems on transistor current components and also the current amplification factors like alpha, beta and gamma. And also we'll see some of the problems on common base amplifier, that is the analysis of or else the calculation of input impedance, voltage gain, output admittance, overall current gain, overall voltage gain and power gain of a common base amplifier using hybrid parameter model. So here, before going to discuss about the problems on this transistor current components, so as we all know that the current equations for in common base configuration, the current equation. So we all know that in common base configuration, base is the common terminal and input terminal is the emitter and output terminal is the collector terminal, right? So we already know that the current equation, that is output current equation of common base configuration, IC is equals to alpha into IE plus IC B naught, where alpha is the amplification factor of common base configuration, IC B naught is a reverse saturation current. It is due to the minority charge carriers, which is less in amount, that is of the order of microamperes, and IE is the emitter current, which is the input current, and IC is the output current. And we also know that in common emitter configuration, we have seen that IC is equals to beta into IB plus ICE naught. So already we know that ICE naught is a reverse saturation current in common emitter configuration, which is equals to beta plus 1 into ICB naught. Okay, so beta plus 1 is also written as 1 by 1 minus alpha, that is equals to ICB naught. And we already know that the relation between alpha and beta, so beta is equals to alpha by 1 minus alpha. Okay, so these are the relations, some of the relations between of transistor current components in common base, common emitter and even common collector. So what is the equation in common collector? So that is in common collector, emitter current is output current and base current is the input current, right? So that is in common collector configuration, IE is equals to gamma into IB plus gamma into IC B naught. Okay, so this is the equation where gamma stands for 1 by 1 plus 1 by 1 minus alpha. So these are some of the relations between some of the current equations of common base, common emitter and common collector configuration. So these are the things that we need to solve some of the problems on transistor currents. So the first one, let us take, in a certain transistor, 99.6% of carriers injected into the base cross the collector to base junction. If the leakage current is 5 microamperes and the collector current is 20 milliamperes, calculate the value of alpha DC and the emitter current. So what are the values that are given? 99.6% of the carriers injected into the base cross the collector to base junction. So that means, so here already we know that in a transistor we have emitter and base. This is base and this is collector. So here the majority charge carriers are generated in emitter and 2 to 5% of the majority charge carriers will recombine here, and the remaining 95 to 98% of majority charge carriers will be entering into the collector terminal, right? So this 2 to 5% of the carriers injected into the or else entered into the base will recombine with the majority charge carriers of the base, which leads to some base current, and these leads to collector current, and the majority charge carriers that are generated in the emitter terminal leads to emitter current. right? So how many electrons are entering into the collector region? 99.6% of the carriers injected into the base will cross the collector. This junction is collector to base junction. In short, we can also call it as JC, that is collector junction. And this junction between a base and emitter terminal is emitter junction. We can represent it as JE. So that means the meaning of this statement is here only 99.6% of electrons are entering into the collector region. So that means IC is equals to 99.6% of IE, because the emitter current is IE, right? So how can we say that the so collector to base junction? So here this IC is equals to 99.6% of IE. Okay, so that means we can say that this is my input current and this is my output current. In which configurations we have input current as IE and output current as IC? In common base configuration. So that means this problem is related to common base configuration. So we already know that the relation of current in common base configuration is IC is equals to alpha into IE plus IC B naught. Okay, and what are the values that are given here? So here IC is equal to 99.6 means 0.996 into IE. So that is IC divided by IE, which we can also define as alpha, that is the common base configuration amplification factor, that is equals to 0.996. This is the value of alpha. So what he asked us to find alpha DC, so which we have calculated it as 0.996, which is defined as a ratio of IC to IE. And now what we need to calculate? We need to calculate emitter current IE. Okay, emitter current IE we need to calculate. So here what are the values that are given? IC B naught is given. So what is IC B naught? That is a reverse saturation current, or else we can also call it as leakage current. That is 5 microamperes. That is 5 into 10 to the power of minus 6 amperes. And IC is also given. That is 20 milliamperes. Okay, 20 milliamperes. Now we need to find out IE. So here, as we all know that alpha DC value is given, and here IC value is known, that is substitute all the values in this one. 20 into 10 to the power of minus 3 is the IC value. Alpha value is 0.996 into IE plus ICB naught value is 5 microamperes, 5 into 10 to the power of minus 6. Now I want to calculate this IE value. So IE, that is 0.996 into IE is equals to 20 into 10 to the power of minus 3. If I take this term this side, then minus 5 into 10 to the power of minus 6. So IE is equals to 20 into 10 to the power of minus 3 minus 5 into 10 to the power of minus 6 divided by 0.996. 0.996. So that you can calculate the value of IC, so IE value. And if I calculate this value, so IE is equals to 20. IE is equals to 20.08 milliamperes. So this is the way we can calculate the emitter current and alpha DC. So that is the first problem in which we have found that alpha DC value and the emitter current value. Just a second. Okay, emitter current value. And now coming to the second problem, calculate the value of collector currents, base current for a transistor with alpha DC is equals to 0.99 and ICB naught is equals to 10 microamperes. The emitter current is measured as 8 milliamperes. So what he asked us to find? He asked us to find IC value and also IB value. So what are the values that are given? ICB naught is given, that is 10 microamperes, and emitter current is given, IE is equals to 8 milliamperes. Okay, and alpha value is also given. So alpha DC value is 0.99. So now we need to calculate this collector current and base current. So as it is given alpha DC, so what is the configuration of the transistor? Common base configuration, because alpha exists only in common base configuration, right? So now in common base configuration, what is the equation for IC? That is IC is equals to alpha into IE plus IC B naught. So we all know all the values of this. Alpha is 0.99 into IE value is known, that is 8 into 10 to the power of minus 3, plus ICB naught is also known, which is 10 into 10 to the power of minus 6. If we calculate this IC, so we can find the value of IC as 7.93 milliamperes. So this is the value of IC. Now he asked us to find even IB also. So we have an equation which shows the relation between all the three currents of a transistor, that is emitter current, base current and collector current. IE is equals to IC plus IB. So we know that IE value and IC value, and we need to find out IB. So IB can be given by IE minus IC. So what is the value of IE? It is already given in the problem, that is 8 milliamperes, minus IC we have got it as 7.93 milliamperes. So the value of IB will be 0.07 milliamperes. 0.07 milliamperes, or else we can also write it as 70 microamperes. Okay, so this is the value of IB. So as you all know that IB will be very less, because IB is very less because it is the current due to the recombination. So where the base is lightly doped, and hence the recombination rate will also be less, and hence we will always have the base current as very less, it is of the order of microamperes. Now the third problem is find the value alpha for each of the following values of beta. Beta is equals to 50 and 190. And also for the value, find the value of beta for each of the following values of alpha, which is alpha is given as 0.995 and 0.9765. So for this, we need to have the relation between alpha and beta. So let us take the first one. So here beta is given, and we need to calculate alpha value. So what is the value of alpha? That is, the equation for alpha in terms of beta is alpha is equals to beta divided by 1 plus beta. So what is the beta value? 50 divided by 50 plus 1. 50 divided by 50 plus 1. So if I calculate this value, I will get the alpha value as 0.98. So that is alpha is equals to 0.98 when beta is equals to 50. And similarly, when I have beta is equals to 190, so similarly we need to find out the alpha value by using the again same formula, 190 divided by 191. Okay, so even if you calculate this value, you will get the beta value as 0.995. So this is the alpha value for the beta value of 190. Okay, so now let us take the second problem. So as the alpha values are given 0.995 and one more value is 0.9765, right? So now we need to calculate the value of beta. So beta is alpha by 1 minus alpha. So alpha is 0.995 divided by 1 minus 0.995. Then I'll get the beta value as 50. I'll get the beta value as, not 50, it is almost 190. And now if I take 0.9765, okay, so then beta value again 0.9765 divided by 1 minus 0.9765, and this will be approximately equals to 49. This will be approximately equals to 49. So that means if a value of alpha is 0.995, the value of beta is 190. That means for a small change in alpha, there is a lot of change in the value of beta. So in order to show that, we have this equation, we have this problem. So now Let us take the fourth problem. So, if the base current of the transistor, so that is the base current is given 20 microamperes, that is 10 to the power of minus 6 amperes, and when the emitter current is 6.4, that means emitter current is also given, whose value is 6.4 into 10 to the power of minus 3 amperes. What are the values of alpha and beta? Also calculate the collector current. So here, as we all know that, so collector current is equals, emitter current is equals to IC plus IB. So if I substitute, so from this I want to calculate IC value, that is the collector current value. So IC is equals to IE minus IB. So what is the value of IE? That is 6.4 into 10 to the power of minus 3, minus IB value is 20 into 10 to the power of minus 6. So if I calculate this one, I'll get the value of IC as 6.38 milliamperes. This is the value of IC. So collector current we have found, that is 6.38 milliamperes. So as IC is known and IB is known, so we can calculate the value of beta. Beta is equals to IC by IB. So where IC is equals to how much? IC is 6.38 into 10 to the power of minus 3, whereas IB is 20 into 10 to the power of minus 6. 20 into 10 to the power of minus 6. So if I calculate this value, so I'll get the value of beta as 311.5. So this is the value of beta. And similarly, if I know the value of beta, I can easily calculate the value of alpha by using the formula beta by 1 plus beta. So the alpha value for this alpha is 311. Beta value is 311.5. 1 plus 311.5. If I calculate this one, I'll get the value of alpha as 0.9968. So this is the way of calculating the alpha and beta and even emitter current and base current. Now let us take the fifth problem. Reverse leakage current of a transistor when connected in common base configuration is 0.1 microamperes. Reverse leakage current of a transistor in common base configuration. It is represented as ICB0. It is given by 0.1 into 10 to the power of minus 6 amperes. Right? While it is 16 microamperes when the same transistor is connected in common emitter configuration. That means here ICE0, that is under common emitter configuration, the reverse saturation is current is given as 16 microamperes, 16 to 10 to the power of minus 6 amperes. Now calculate the value of alpha and beta. Calculate the value of alpha and beta. So for that, first of all, we all know that the relation between ICE0 and ICB0 as beta plus 1 into ICB0. That is ICE0 is equals to beta plus 1 into ICB0. Okay. So now here we all know that ICE0 value is 16 into 10 to the power of minus 6, whereas ICB0 value is 0.1 into 10 to the power of minus 6. So and hence we can calculate beta value as, or else beta plus 1 can be calculated as beta plus 1, right? 16 into 10 to the power of minus 6 divided by 0.1 into 10 to the power of minus 6, right? So if I calculate this beta value, this is this one get cancelled. So here if I take this point out, so this is 160 minus 1. So how much? 159. This is the value of beta. 159 is the value of beta. And now if I know the beta value, I can easily calculate the alpha value as alpha is equals to beta by beta plus 1. 159 divided by 159 plus 1. So in this case, I'll get the value of alpha. If I calculate this value using the calculator, I can get the value of alpha as 0.994. So that is alpha is equals to 0.994, where beta is 159. So these are some of the problems on transistor current components and also the amplification factors alpha, beta. Now let us see some of the problems on common base amplifier. So first of all, how to do the AC analysis for a transistor circuit. We have some steps. What are that means any transistor amplifier circuit is given. If I want to do some AC analysis in the sense when the under the application of AC signal, we are going to calculate the input impedance, output admittance, voltage gain, current gain. So for that, first of all, we need to have equivalent circuit. In order to get the equivalent circuit, this is the procedure. So what is the procedure here? Draw the actual circuit diagram, whether it is a common base configuration or common emitter or common collector. Draw the actual circuit diagram. Replace all the coupling capacitors and emitter bypass capacitor by short circuit. So if any capacitors are there, as we are doing AC analysis, just short circuit all the capacitors, coupling capacitors. And now replace the DC sources by a short circuit. Whenever we will do AC analysis, all the DC sources should be short circuited. That means all the DC sources should be made zero. Okay. In other words, short circuit VCC and ground lines. Next, mark the base, collector and emitter terminals of transistor on the circuit diagram and locate these points as the start of the equivalent circuit. So first locate the terminals of transistor and then replace the transistor by its H parameter model and then do the AC analysis. These are the steps we need to keep it in mind. Okay. And we already know the formulas of voltage gain, current gain, input impedance and output admittance of a transistor by using hybrid parameter model. So that is the current gain formula is given by minus HFE. If we consider it as a common emitter configuration, the formulas are minus, or else in general we can write it as minus HF by 1 plus HO into RL. And input impedance is given by HI minus HF HR divided by HO plus 1 by RL, or else we can also write it as YL. Okay, 1 by RL is nothing but admittance, so we can also write it as RL. And voltage gain is given by AI into RL by RI, where RL is the load impedance connected to the transistor, and output resistance R naught is equals to RS plus HIE divided by RS plus HOE plus delta H, where delta H is given by HIE minus HIE HOE minus HRE HFE. So these are the formulas that we need to remember whenever we are solving the problems on amplifiers. And one more thing, we also need to remember the H parameter values. If the H parameter values are not given, so we need to use the ideal values of H parameters of all the three configurations. So that is why these H parameter values are also should be remembered. Okay. Now coming to the conversion formulae. So as I want to discuss only common base configuration problems in this lecture, so I just want to show you the conversion formulae for converting H parameters from common emitter configuration to common base configuration. That means if I know the H parameters of common emitter configuration like HIE, HFE, HRE, HOE, how to derive the values of H parameters of common base configuration. So for this, these are the conversion formulae. HIB is equals to HIE by 1 plus HFE, and HRB is equals to HIE into HOE by 1 plus HFE, that is equals to minus HRE, and HFB is equals to minus HFE by 1 plus HOE, and HOB is equals to HOE by 1 plus HOE. These are the formulae that are used to convert H parameters from common emitter configuration to common base configuration. We need to remember. That means if common emitter parameters are given, I want to solve the common base configuration, then I have to first convert the hybrid parameters into common base configuration using this conversion formula. So this is the first problem on transistor parameters. So a common base circuit has the following components. RS is equals to 1.5 kilo ohms and R1 is equals to 100K. R2 is equals to 10K. RC is equals to 5K. and the H parameters are HIE is equals to 1.2K and HRE 2.5 into 10 to the power of minus 4. This is 10 to the power of minus 4, power of. HFE is 55. HOE is 25 microamperes per volt. Draw the equivalent hybrid model and calculate AI, RI or not AV, and also I want to include two more parameters, AVS and AIS. Okay, so these are the parameters that we need to calculate. So as it is given, if you observe, it is given H parameters of common emitter configuration. So first of all I need to convert this into common base configuration using the conversion formulae. So that is HIB is equals to, so what are the conversion formulae we have? HIE plus HIE divided by 1 plus HFE. HIE divided by 1 plus HFE. So what is the HIE value? 1.2 into 10 to the power of 3 divided by, next HFB is minus HFE by 1 plus HFE. HFB is minus HFE by 1 plus HFE. What is the HFE value? Minus 55 by 1 plus 55. Right? Next, HRB. HRB is HIE, HOE by, or else HRB is minus equal to HRE. HRB is equals to minus HRE. So what is HRE value? HRE value is minus 2.5 into 10 to the power of minus 4. And now coming to the HOB, HOE by 1 plus HFE. So HOB value is HOE by 1 plus HFE. So what is the value of HOE? That is 25 into 10 to the power of minus 6 divided by 1 plus 55, because HFE value is 55. Now let us calculate all these values here. HIB is equals to 22 ohms. Not 22 exactly. It is 21.42 ohms because it is input impedance. Input impedance is always measured as ohms. And coming to HFB, the value of HFB is minus 0.98 because we have minus here 0.98. HRB value already we have calculated, minus 2.5 into 10 to the power of minus 4. And HOB value, so HOB value after evaluating this value 0.45 into 10 to the power of minus 6 amperes per volt, because it is admittance. The units for admittance are amperes per volt. Now first of all, let us try to draw the equivalent circuit. First of all, let us try to draw the circuit diagram of common base configuration, right? So common base. So this is the common base configuration where base is the common terminal between the input and output. So at the output side we have RC, okay, RC, and we do have biasing here. The biasing will be like this, plus and minus. Okay, and then at the input side we have R1 in parallel with R2. Okay, so as we need to provide the biasing such that emitter to base junction is forward bias, this is R2 and this is R1. Those two are in parallel here. This is RS in series with the voltage source, that is plus minus Vs, and this is RS. And here the current, emitter current is flowing, IE, and IB is flowing, and here IC is flowing, right? And we do measure the output voltage across this one collector terminal, okay, and we do measure the input voltage across this one VI, right? So this is the equivalent circuit. So according to the steps I have given, first of all I want to draw the equivalent circuit by replacing the transistor, right? So I want to replace the transistor by its H parameter equivalent circuit by making the voltage sources ground. So if I make this voltage source as 0, this will be connected directly to the ground. This is also connected to the ground. We don't have any capacitors, so I am not considering it here. So now the equivalent circuit of this, we do have RS and we do have Vs here. This is Vs plus minus and this is RS, and R1 and R2 are connected in parallel here. R1 R2. And now I'm replacing the transistor. What is the input terminal? Emitter terminal is the input terminal, to which the equivalent circuit will have HIB, okay, in series with an voltage source, okay, plus minus, and the magnitude of this one is HRB into VC. This is the VE. This is nothing but emitter voltage, and this is IE, emitter current, right? Now coming to the output side, we have a current source, dependent current source, whose magnitude is HFB into IE, okay, HFB into IE, and here we do have HOB, and the current flowing through this one is IC, because this is the collector terminal and this is the base terminal, which is ground, right? To this one we have RC here, RC, okay, across which we are taking the output, which is nothing but VC, okay. So now here, this is my circuit. So here if I take this one, these are the two resistors which are connected in parallel, and I am considering the parallel combination of R1 and R2 as RE, R1 and R2 as RE. So that means here all the values are given. What are the values? R1 is given, just a second. So R1 is given, R1 is equals to 100K, and R2 is equals to 10K, and next RS value is also given, that is 1.5K, this is 1.5K, and RC value is 5 kilo ohms. So these are the values given, and we have already find the values of H parameters here. So now the first thing what I want to do is I want to calculate the current gain. So first of all, the formula for current gain is minus HFE by 1 plus HOE into RL. So what is RL here? We have RC only RC is given. So across this RC only we are taking the output. RL is equals to RC. So minus HFB. This is common base configuration, right? B we have to use. HFB value is minus 0.98 divided by 1 plus HOB. What is the value of HOB? 0.45 into 10 to the power of minus 6 into RC. What is the value of RC? That is 5 into 10 to the power of 3. So here if I calculate this value, I'll get the current gain AI 0.982. This is the value of current gain, right? Now after the current gain, I want to calculate the value of RA, because already we have the formulas. What is the formula for current gain? That is input impedance, that is HIB plus HFE, HFB, HRB, or else just a second, HIB plus HRB into AI into RL, AI into RL. So here HIB value we know. What is the value of HIB? 21.42 plus ohms it is, plus HRB value is minus 2.5 into 10 to the power of minus 4 into current gain value is 0.98 into RL value is 5 into 10 to the power of 3. So if I calculate this input impedance, so if I evaluate this value, I'll get the input impedance as 22.65 ohms. This is the input impedance. So input impedance is the impedance that is seen when we are looking into this terminal and input port, and this is called as Ri dash. So where Ri dash is equals to Ri in parallel with Re. This is the equivalent impedance, right? If I replace the circuit with equivalent impedance, then these two will be in parallel. So Ri in parallel with Re will be equals to Ra dash. What is Ra? That is 22.65 into Re value is known. So that is we have already calculated. Re value, we didn't calculate it till now. So Re is nothing but, okay. Re is nothing but R1 in parallel with R2. So that is 100K into 10K divided by 100K plus 10K. So this is the value of RE. So if I evaluate this value, RE will be 1.28. Let us write here the value of RE. Here only I am writing. RE value is 1.58 into 10 to the power of 3 ohms, or else 1.58 kilo ohms. So this is the value of RE. So RE, that is RA is 22.65 and RE value is 1.58 into 10 to the power of 3. So if I calculate the parallel combination of these two resistances, I'll get the RA dash 20.7 ohms. 20.7 ohms. So this is the value of RA dash. So we have calculated current gain and input impedance. Then voltage gain. So we are going to calculate the voltage gain. So AV is equals to AI into RL divided by RA. AI into RL divided by RA. So the voltage gain formula. So already we have calculated the current gain. So what is the current gain we have got? That is 0.98 into RL is 5 into 10 to the power of 3 and RA. What is the value of RA? 22.65. 22.65. So if I calculate this value, I'll get the voltage gain, and the voltage gain value is 216.77. This is the voltage gain, right? Now let us calculate AVS. What is AVS? AVS is the voltage gain by taking the source into consideration. So first of all, let us draw the Thevenin's equivalent circuit of input. So already we have RS in series with voltage source. So we have RS. So if you look at this diagram, so if I can replace this entire circuit with RA dash, right? So where RS will be in series with RA dash. So here now I can have RA dash, as in parallel the voltage is same. The voltage measured across RA will be VE, and this is RS, and here this is nothing but voltage source plus minus Vs. Now apply the voltage divider principle. First of all, AVS can be written as V0 divided by Vs, and I am multiplying and dividing this one by VE. So then V0 by VE into VE by Vs, right? So here V0 by VE is AV into VE by Vs. Now I want to find out VE by Vs by this. VE divided by Vs can be written as, or else we can write VE is equals to, according to the potential divider principle, input voltage into that resistance RA dash divided by RS plus RA dash. So now here substitute this one in the above equation. So AVS can be given by AV into RA dash divided by RS plus RA dash. So what is the value of AV? That is 216.77, which we have calculated from this, into RA dash value just now we have calculated 20.7, and RS value is, what is the value of RS? The RS value is given in the problem, that is 1.5K. That is 1.5 into 10 to the power of 3 plus 20.7. So if I calculate this AVS value, if I evaluate this value, I'll get the AVS as 296. AVS value is 296. So this is the value of AVS by taking the voltage source into effect. And similarly, AIS we need to calculate. AIS can be calculated as so by taking the source into effect, IL by IS, and we are multiplying and dividing this one by IE. So IE by IE. So what happens? IL by IE is nothing but current gain without considering the source into effect into IE by IS. So here IL by IE is AI into IE by IS. We need to calculate this IE by IS. So for that, I am just converting this into current equivalent, Norton's equivalent circuit. In Norton's equivalent circuit, we'll have a current source. in parallel with a resistance, that is Rs, and in parallel with Ri. In parallel with Ri. Okay. So here now, Ri. So now here this is nothing but my current. Re is there before that, and we have Rs is also there. So here I want to calculate this IE, which is the current flowing through Ra. So according to the current divider principle, the current through the resistance Ra can be found out by taking this into effect. So that is input current into opposite resistance. What is opposite resistance? Re divided by Re plus Ri. Okay. So here now from this I can have IE by IS is equals to Re divided by Re plus Ri. Okay. So now AIS can be calculated as AI. The AI value is 0.98 into Re value. What is the Re value? We have got R1 in parallel with R2. What is the value of R1 in parallel with R2? That is 1.58 into 10 to the power of 3 into 10 to the power of 3 divided by 1.58 into 10 to the power of 3 plus here this Ra value we have got it as 22.65. 22.65. If I calculate this AIS, value will become now 0.979. So this is the value of current gain by taking the source into effect, source resistance into effect. So this is the voltage gain. Now find out R0. So R0 value can be given by 1 by HOE minus 1 by HOB minus HRB into HFB divided by HIB plus RS dash. HIB plus RS dash. So here what is RS dash? RS dash is equals to RS in parallel with RE. What is RS? That is 1.5 into 10 to the power of 3 into RE value is R1 in parallel with R2. How much we have got? R1 in parallel with R2. That is 22.65. That is 1.52 kilo. This is 1.58 kilo. So 1.58 into 10 to the power of 3 divided by here parallel combination, right? 1.5 into 10 to the power of 3 plus 1.58 into 10 to the power of 3. So if I calculate this RS dash value will be 1.28 into 10 to the power of 3. This is RS dash value. So now substitute all the values in this one, as we all know that values of HOB. What is HOB? 0.45 into 10 to the power of minus 6. Okay. And then minus HRB. HRB is minus 2.5 into 10 to the power of minus 4 into HFB is HFB value is minus 0.98 divided by HIB. HIB value is 21.42 plus RS dash is 1.28 into 10 to the power of 3. If I calculate this value, I'll get R0 value as 3.68 mega ohms. So this is the value of R0. So R0 is equals to 3.68 mega ohms. What is R0 here? Actually, it is a impedance that is seen when we are looking into the output port. 3.68 mega ohms. So similarly, this is not by considering RL. So by considering RL, we can have R0 dash, that is RL in parallel with R0. That is RL is nothing but RC. What is the value of RC? We have 5 kilo ohms. In parallel with R0 is 3.68 mega ohms. If I calculate this value, I'll get R0 dash as 4.99 kilo ohms. So this is how we can evaluate all the parameters of common base amplifier using H parameter model of a transistor. Okay, so here this is a problem we have, that is compute the current gain, voltage gain, input output impedance of the common base amplifier. If it is driven by a voltage source of internal resistance Rs and load impedance of RL, the transistor parameters are all given here. Okay, and this one. So now calculate current gain. So already we have the formulas here. So what are the formulas? AI is equals to minus HFB by 1 plus HOB into RL. So here RS is given. What is the value of RS? 1 kilo ohm, and RL is given, that is 1 kilo ohm. Okay, both are 1 kilo ohms. So just substitute that values and find out AI. And similarly RI. What is RI? HIE plus HFE, HIB plus HRB into AI into RL. AI into RL. So we all know this. HIB value, we know HRB value is given. Substitute all these values, we can find out RL. And similarly AV, as we have calculated AI here, use that AI into RL divided by RI. AI into RL divided by RI. So from this you will be calculating AI. RL you know, RI you will be calculating from this. Substitute and find out AV. And similarly R naught value, that is 1 by HOB minus HFB into HRB divided by HIB plus RS dash. What is RS dash? RS dash is nothing but okay, we don't have any other resistors, no need to calculate RS dash. Whereas in the previous problem, as the two more resistances are given, R1 and R2, so we have taken these two are in parallel with RS, so we have calculated that. But here, as no other resistance is given, only RS value is given, so just substitute all these values here. HOB minus HRB into HFB divided by HIB plus RS. So just substituting, we can all calculate these values. So this is the way we can solve the problems given on common base configuration, that is common base amplifier. I hope it is clear to you all. If you have any queries, you can post it in the comment section so that I can revert back. That's all for this lecture. Thank you, one and all.
Like, share and subscribe. Hit the bell icon for more updates.